Okay. So let's reread this for the 15th. We'll also use thread event delivery in place of their existing operation. Okay, so we don't use IDT anymore. Cool. Thread return instruction. Two new return instruction. ERET S, ERET U, effect return from event handling. ERET S, event return to supervisor, is designed to return event incident to ring 0 and does not change the current privilege level. ERET user, event return to user. Ah, that's why the E is there. Okay. Event return to user returns the application software operating in returns to application software operating in ring 3. Yeah, so that's what I was saying when I was saying that it looks like it only handles ring 0 and ring 3. But I guess there's magical ways to do other things. Or maybe the standard offers place for like things down the line. Oh, it's explained here. I should just shut the fuck up and read. GS segment management, thread transitions that change the CPL, thread event delivery. Sorry. And event return user, update the GS base address in a manner similar to the swap GS instruction. Okay. In addition, the LKGS instruction allows system software to manage GS segment more flexibly. Oh, I guess that's because GS is one of those register that will need to be updated sometime just by changing stack. GS.base. Oh, I guess that's it. The MSR with address or FS and GS. Okay, yeah, I guess it's just handling of. It's just that it can change with the stack that it's in or with the process or whatever the fuck we call it. Okay. When thread transitions are enabled, they are only ring. God damn! Wake the fuck up. Okay, there are the only ring transition possible. Oh my god, the wording! Holy shit! When thread transitions are enabled, they are the only ring transition possible. Since thread event delivery is always to ring 0 and our event return to user returns only to ring 3, it is not possible to enter ring 1 and ring 2 while thread transition are enabled. Enabling thread transition also prevents entry to compatibility mode in ring 0. Okay. It sounds important. The thread architecture is defined for use by 64-bit operating system, except where noted. Changes to this processor behavior and new instruction apply only in the IA32E mode, and not in legacy protected mode or real mode. The new processor state defined by the thread architecture is accessible with MSR access instruction, regardless of the mode. What does those thing do? Will we have an idea here? No? Guess we'll look into it. Ah, don't start searching! It's searching too hard! Look at it painting. Oh, really? Oh, that's cute. Oh, I like that. Oh, I like that page. I like that. Okay. So it's for a model specific register. Okay. Oh, it's already bookmarked. But yeah, when I saw that it was like the full fucking thing, combined volumes, I was like, uh, no, but I mean, everything seems to be done so that we can research it easily, so I won't have to waste my time bookmarking it. I think that the only big issue is that, you know, you know what? We will need this in kernel info, okay? Fuck the Intel copyright. We just we just get all of this. We'll scrub this too, and we'll explain even deeper, okay? That's the plan. Oh fuck, I refreshed. Okay. We're at like 154. Yeah, here we are. Okay, cool. Cool. The thread architecture introduced the concept of the stack level. The current stack level, CSL, is a value in the range of 0 to 3 that a logical processor can track when CPL equals 0. I added can. Why? I'm sorry if you hear something in the background. My neighbor is doing his lawn. That a logical processor tracks when CPL equals 0. Thread event delivery determines the stack level associated with the event being delivered, and if it is greater than CSL or CPL had been pre, load the stack pointer from the new thread RSP MSR associated with the event stack level. I hear the multiple fans in my room. Are you memeing right now? Are you memeing? You are memeing, okay? You're talking about you you memer. No, I can hear my AC. I got it. No, I'm surprised. But he's got electric tools, so he's cool like that. Okay. Load the stack pointer and then you okay. All right. So if my understanding is correct, wait. No, I'm being retarded. Wait. We will listen what we said yesterday. Just read. Okay. From the new thread RSPMSR associated with the event stack level. If supervisor shadow stacks are enabled, the stack level applies also to the shadow stack pointer SSP, which would be loaded from the thread SSP MSR. The thread return instruction return system restored the old stack level. Return the old stack level. Lol. Okay. The existing shadow stack architecture includes a token management mechanism to ensure shadow stack integrity when switching shadow stacks. This mechanism uses locked read modify write operation that may affect worst case performance adversely. Thread transition do not use this token management mechanism and instead protect shadow stack integrity by having the thread return instruction check value in the thread SSP MSR. Because thread transition do not use the shadow stack token management mechanism, thread event delivery can never cause a fault or a VM exit after setting the buzzy bit in the shadow stack token, unlike IDT event delivery. For that reason, an OS that enables thread transition need not consult CPU ID before enabling supervisor shadow stack. Okay. Or enumeration, enabling, and configuration. This section describes the enumeration, enabling, and configuration mechanism for the thread architecture. Enumeration. The thread architecture includes two related but independent elements, the new thread transition and the LKGS instruction for management of the GS segment register. Because 64 bits operating system may benefit from the LKGS instruction without using thread, the two elements are enumerated independently. Okay? Oh, okay. So, yeah. Is the new feature flag that enumerates support for the new thread transition. It also enumerates support for the new architectural state, MSRs, defined by thread. LKGS is a new CPU ID feature flag that enumerates support for the LKGS instruction. NMI SRC is a new CPU ID features flag that enumerates support for the NMI source reporting. Any Intel processor, Intel copyright registered processor, that enumerates support for thread transition will also enumerate support for LKGS. Okay, so the two come together, but they can be enabled independently. Cool. Enabling in CR4. Software enables thread transition by setting CR4, henceforth CR4.thread. Specifically, enabling CR4.thread enables thread event delivery as well as thread return instructions, although those instructions can only be used in 64-bit mode when cs.l equals 1. Oh, cs long, right? Execution of the move to CR4 instruction outside of 64-bit mode, clear CR4. Okay, so it clears the upper 32-bit. For this reason, software must first enter 64-bit mode before using move to CR4 to set the CR4.thread. The architecture ensures that CR4.thread can be won only if the logical processor is in IA32E mode. Yeah, it would make sense, or else how the fuck would you be able to set the bit, the upper 32 bit? As just noted, move to CR4 can set CR4 thread only in IA32E mode. Software can leave IA32E mode only by executing move to CR0 to attempt to clear the CR0 PG, and this can be done only in compatibility mode while CPL equals 0. What? Give me a moment. Oh man, sorry. Give me another moment. My ADD is compelling me to play video games. I need to focus. Okay, software can leave IA32E mode only by executing move to CR0 to clear CR0.pg, and this can be done only in compatibility mode while CPL equals 0. Attempting to clear CR0.pg in 64-bit mode will fault. Okay, I have a question. Maybe you have the answer, or maybe I should just Google, but when we execute a 32-bit software on Linux, we don't actually switch to compatibility mode on the CPU, right? It's just like the kernel doing its compatibility thing. The CPU won't switch mode. When Linux is running, that's an AI question. I don't know, but I would think the CPU switch mode. You see, that was my assumption, but right now, from what we're reading, we would need to be in CPL equals 0, which would mean kernel mode, but you see, that feels wrong to me. Lol. Okay, so, hi, whoops. Hi, I'm trying to understand x86, 64, based on, and based on Linux. My question is, maybe I shouldn't space this shit out a bit more. Okay. My question is, when executing 32-bit software on Linux, does the CPU go in compatibility mode, or does it stay in IA32E and the kernel does the work? Because some instructions don't return the same result in 32 bits and 64 bits, so I don't see how the kernel would override the compiled code. Well, I'm assuming that the compiled code would use the register name like in 32-bit, so somehow it would know. Oh, fuck. We're retarded. Oh, maybe not. Wait, that's an excellent question that gets right to the heart of the modern operating system interact with x86 hardware. If you are reading the Intel 64 and the terminology can get incredibly dense. No shit, Sherlock. The short answer is actually both. The CPU remains in IA. Yeah, that's where I was going to. Okay. In IA32E mode, but overall, it executes that specific 32-bit process in compatibility mode. Because compatibility mode here means two things. There's compatibility mode within IA32E. Yeah, I'm sorry, now the sound is worse. Anyway, within IA32E, and there's the one outside of IA32E, which doesn't freaking help in making things clear. Goddamn. Okay, the architecture of IA32 E mode. According to the Intel SDM, what do they mean by that? Source thing manual? Software developer manual. Okay, nice. According to the Intel software developer manual, am I retarded? Okay, software developer manual, IA32E is the overarching long mode that enables 64-bit computing. However, IA32E is not a single state. It is divided into two distinct sub-mode. 64-bit mode, used by the 64-bit Linux kernel and native 64-bit user application. Compatibility mode, a sub-mode that allows legacy 16-bit and 32-bit application to run without recompilation under a 64-bit OS. Because compatibility mode is a sub-mode of IA32E, I don't like that it quotes this, but okay, is a sub-mode of IA32E, the CPU never leaves IA32E. It doesn't drop all the way back to legacy protected mode. Oh, okay. Oh, okay, I think I get it now. Paging remain enabled, physical address space remain expanded. Oh, that makes a lot of sense. And when we're talking about long, or that's what we're talking about that. Okay, so when they're talking about the long bit, they're talking about being in 64-bit or not. Okay, so that's why we should never leave that mode, unless your OS is trying to commit suicide or something. Okay. If cr4.thread equals 1, it is impossible to enter compatibility mode while cpl equals 0. Okay. Wait. What the fuck? What do they mean by compatibility mode? Oh, yeah, thread is not compatible with 32-bit things. So that would mean that if we want to execute anything 32-bit, we have to disable thread. Wait, really? Well, actually, that's logical. But that sounds like a crazy amount of management just to keep 32-bit compatibility. But I guess, fuck you, that's the job of the software. Yeah, that would make sense. RSM and VMX transition. I have no fucking clue what they mean by that. Or maybe they talk about it here. No, they don't. Okay, cool. Virtualization. Okay. And for the other one, RSM, resume from system management mode. Okay, sounds important. It is. Cannot enter a state in which CR4 thread equals 1 while outside. What? Let's read that again. RSM and VMX transition cannot enter a state in which CR4 thread equals 1 outside of IA32E mode. Well, that's already the case, right? You cannot set it. You cannot set this unless you are already in 64-bit mode. Like that's what this is talking about. This. So I don't really get this, but I guess what they're saying is you're going to break some shit if your thing is set, if thread is set to 1, and you, which should be impossible in the first place, but hey, who cares? The value of cr4.thread does not affect, it's probably useful for someone that actually like programs the stuff. The value of cr4.thread does not affect the accessibility of the new MSR. Okay, so we will, even if you don't technically have thread enabled, you could use the registers, okay? By MSR access instruction, nor does it affect the operation of the new LKGS instruction. We knew that. Enabling thread transition changes the behavior of various existing instructions, see section 8. Okay. Starting to like it. New MSRs for configuration of thread transition. Thread transition are controlled by the following new MSR, IA32 thread config. This MSR is organized as follow. Bit 1, the first 2-bit. This MSR contains the current stack level. This is a 2-bit value manipulated and used by thread event delivery and the thread return instruction. Software can modify the CSL with the MSR write instruction, but this is not an expected usage. It is recommended that when using such an instruction to update IA32 thread config, software always write the existing CSL into bit 10 of the MSR unless it is specifically desired to change the CSL. Bit 2 is reserved. Bit 3, I'll be so happy whenever we have a system where we can just like make graphs with this very easily. Did I just click something that has a link in it? Bro, I need to stop yapping. Bit 3 indicates if set that if thread event delivery is not changing stacks, it should decrement the shadow stack pointer by 8. Okay, shadow stack handling, so let's ignore it. Bit 5 and 8 are reserved. 8 to 6, identify the amount. Those are inclusive number, by the way, okay? Identifies the amount measured in 64 byte cache lines by which Fred event delivery decrements the regular stack pointer when not changing event stacks. So, oh, okay, this would be the amount of, like when we're talking about, like green is for the stack. You know what? I just need to fucking write for real. Green is for the stack and blue is for Fred. So this, let's just copy this. I'm lazy. And it's 8 to 6. Whoops. 8 to 6. Bro, I'm retarded. Size. Okay, so the size of this Fred thing is determined by this config. Bit 10 to 9 identify the stack level that is used for maskable interrupt that are delivered in ring 0. Okay. Bit 11 is reserved. Bit 63, so the last bit to 12, contains the upper bit of the linear address of the page in memory containing event handlers. Okay, so where do we go and get our event handlers? Fred event delivery will load RIP to refer to an existing return instruction pointer. Okay. Fred event delivery will load the return instruction pointer to refer to an entry point on this page. Okay. So if we have an event, we can reference this to know where to go get our information. Okay, I think we're getting it. A write to this MSR causes general protection exception if its source operand is set to any reserved bit or if it is not canonical relative to the processor's maximum linear address width. Okay. IA32 Fred RSP 0, 1, 2, 3. Blah, blah. These are the Fred RSP, so return stack pointer MSRs. If Fred event delivery causes a transition from ring 3 or a change to the CSL, so the current stack level, it loads the RSP from Fred RSP MSR corresponding to the new stack level. Okay, I not understanding everything here, but I think we'll get there. Like for now, it's already making more sense, right? All right, do any of these MSRs using right MSR cause a general protection exception if its source operand is not 64-bit align, bit 5 to 0 are not all zeros? Okay, 64 byte align. Oh, okay, I think I get it. So it means that the first 6 bits needs to be zeros because like size in bytes binary. Shit, that's not what I want. Okay, fuck it. 512. So that means that is. I'm retarded. I'm so retarded. Okay, so this is 1. This is 2. This is 4. This is. Again, I'm fucking retarded. 8. This is 16. I hate fucking things up like this. This is so dumb. Why can I just not express? 1, 2, 4. I should have this on speed dial. Okay, should have this somewhere. 16, 32, 60, 64, 128, 256, 512. Okay, this makes no fucking sense. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, we start here, right? We start here. So 1, 2, 3, 4, 5, 6. Okay, now it makes sense. Okay, so let's actually just make it clear. Okay, cool. Okay, makes sense. We're pointing to octets, to bytes, not to bits. And also, how cool is it that in French we use octet? I like this so much more than the bit-byte dilemma. Like it fucks with your mind. Okay. Number 0 to 3 of the MSR name refers to the corresponding stack level and not to the privilege level. Cool. But it would be cool if we know what the fuck stack level means. IA32 Fred STKLVLS. Okay. Store current level of stack. This MSR is interpreted as an array of 32 2-bit values. French computer words are based generally. Yeah. It feels like, well, the Latin root for everything that we do in French is always superior to the weak Germanic root of the English language. That sounds like an insane racial argument that I'm making here, but fuck it, I'll make it anyway. One for each vector in the range 0, 31. For an exception in the for an exception with vector v, or for a non-maskable interrupt in which it has a vector of v equals 2, occurs in ring 0, Fred event delivery ensures that each new stack level is at least the value of Fred v 2v plus 1 2v. Okay, so we're taking 2 bits out of it. I'm not sure if I get what the fuck we're talking about. So is this like a way to be able to choose which vector, so where to go with an interrupt or with an exception linked to this, right? So this gives us the general address, and this will give us like the precise like range, and this is the actual vector, I think. But it's 2 bits. Isn't that a bit shallow? Let's read this again. I'm not sure I understand. And is this like part of a note? No, it's not part of a note anymore. Okay. IA32 Fred STKL VLS stack levels. This MSR is interpreted as an array of 32 2-bit values, one for each vector in the range 0 to 31. For an exception with vector v, or for a non-maskable interrupt which always has a vector of v equals 2, that occurs in ring 0, the Fred event delivery ensures that a new stack level is at least the value of... Oh, okay, I think I get it. So this is, this seems to be which segment, not the offset? I don't think so. I think that this is, essentially, we have a concept now called stack level, and this is a big array that tells you if you want to use this vector, you need to have this stack level. So you have like all of these values bundle in, where it will give you the stack level required to run this specific thing inside of your register. Because it's 2-bit. So 2-bit, that can be either the stack level or the current or the protection level or whatever the fuck it's called, or the ring level. And it says, I'll die. When I click on thing, it transfer me. So it says, for an exception with vector v, it goes there. I guess fuck, let's see it. Determine the new value of stack level RSP or SSP. Can we... Okay. If the event exception of non-maskable is event, stack level is where v is the event's vector in range 031. The stack level of all other event is 0. So essentially the first 32 events are events that you need to check this in order to know the stack level. And if we go and check the IDT, because I believe they said that they didn't change the amount of things that you can store in the IDT. Like it's still based on that same thing. So if we go check the IDT, is it that the first 32 have something important to them and the other are external? That looks like it. So everything in this like special place for the IDT and now for Fred, it has a specific handling where I guess you need to specify the stack level at which it can be run, while everything else, you just assume that it's an external interrupt, so it's handled in the same way. So that's why it assumes 0. All right, that makes a lot of sense now. Let's go back. If I'm not making sense at any point, tell me, all right? IA32 Fred SSP 1, 2, 3. Oh, we don't have 0 here. Oh, it's shadow stack pointer. Okay. Getter with existing shadow stack pointer. These are Fred shadow stack MSRs. Okay, I don't care about shadow stack for real. With the Fred RSP MSR, the number 0 to 3 MSR name refer to the stack level, not the privilege level. Like you said, they really don't want us to get this shit mixed up. The Fred SSP MSR is supported by any processor that enumerates CPU ID Fred. Okay, so if you have Fred, you have shadow stacks. If such a processor does not support CTE, Fred transition would not use the MSR because shadow stack are not enabled, but the MSR would still be accessible using the MSR access instruction. I guess that bit is in there for AMD, right? Saying that you can work without CTE, which is a strictly Intel thing, right? Yeah, CET, sorry. Not getting it in the head very hard. The reset state of each of new MSR is 0, and it does not change the value of the new MSRs. Okay. Fred use of existing MSRs. In addition to the new MSRs identified in section 4.3, Fred transition use several existing MSRs as specified in the following item. IA32 star. What the fuck is this? System call, transition, algorithm, return. No, okay. Maybe it's a good idea that we search what the fuck this is. It's a system call related thing. Let's wait half an hour for an answer. Okay, back in this. We're in Fred right now. While being in the 64 manual. If the value popped out of the stack corresponds to the value of IA n plus 16. Okay, not sure if it helps me in any way. Operation when Fred transition are not enabled, syscall load the CS and SS register with the value derived from bit 47 and 32 of the IA32 star MSR. However, the SS and CS descriptor cache does not load. Descriptor caches are not loaded from the descriptor in GDT or LDT referenced by those selector. Instead, the descriptor. I'm confused how this helps me in any way. Shit. AI, come. What is the... Okay, the IA32 star system target address register is a model-specific register MSR located at address this that act as an hardware configuration file for fast system calls on x86-64 processor. To understand why it exists, you have to look at the older int 0x80 software interrupt mechanism. Software interrupts are notoriously slow because the CPU must read the interrupt descriptor table, IDT, and the global descriptor table, GDT, from RAM to figure out the kernel's privilege level, code, segment, and memory location. The system call and system read instruction were introduced to bypass the memory entirely. Instead of reading from RAM, the CPU reads the segment selector directly from IA32 star register cached right into the CPU silicon. Okay. So this sysret, syscall, hold the base of the offset that calculate the user space string tree codes. Okay. In legacy 32-bit mode, this 32-bit memory address. Okay. Okay, so that might be interesting. Let's just read how the Linux kernel sets it up. During the boot process, the Linux kernel has to initialize the CPU core. It starts by the write MSR assembly instruction to pack the offset of its GDT entry. Global descriptor, what's the name? Global descriptor table. Entries into IA. Can we have a look at the GDT? I like when we're talking about things as if... fuck. I feel that we're doing like the missile knows where it is. It's a core part of Intel x86 architecture that helps manage how memory is accessed and protected. Introduced with Intel 8286, it plays a role in defining memory segment and their attributes. Is there a way to say this? And am I fucking it up? Intel 8286, that's how you would say it, right? You sound knowledgeable with all those acronyms. Yeah. That is it. Okay, 8286. I just want to be sure because, like, sometimes people will say things, and because they don't say it correctly, they feel retarded. Like if someone was to say x86 instead of x86, that would be weird, right? And I don't want that weirdness happening in my videos. Because even if we did research, it would show like that I'm incompetent. x86 sounds AI, yeah. It plays a role in defining memory segment and their attributes, the base address, the size, the access privilege, like it's Yeah, but that's I'm kind of conflicted with this because the explanation that we had here, like this makes sense for 32-bit, but 64-bit, we don't really use CS and SS in the same way. Even though modern 64-bit system rarely relies on segmentation, the GDT remains a required component for starting up the processor and managing certain system-level tasks. The GDT helps isolate memory between application software and operating software. In protected mode, a more advanced processor mode that allows memory protection, the GDT define code segmentation, regions of memory that contains executable data, data segmentation, areas used to store data, system segment, like the task state segment, which is used for multitasking support. Each entry in the GDT is either 8 or 16 bytes long and holds the segment descriptor that defines the property of one segment. Each descriptor includes access right, ensuring the program cannot modify protected memory. Okay. Yeah, I guess that's my question. GDT in 64-bit. In 64-bit mode, segmentation is mostly disabled. All segment base are treated as 0, and the limits are ignored. I need to fucking sneeze. Okay. All segment bases are treated as 0. So this is treated as 0, and now it becomes only like a configurator, I guess. And limits are ignored, okay? Creating a flat address space. However, GDT is still required to define system descriptors such as the task state segment, two segment register, FS and GS, remains active and are often used by the operating system for thread local storage or processor specific data. Okay, so I guess that if we go in there, maybe not. Okay, who cares? Who cares? Let's read this again. Okay, cool. So this is mostly useless. Nice. All right. So this is essentially a pointer to our actual like events, I think. This MSR is used by existing operation of syscalls and systhread. It's a pointer to those, right? Thread uses thread event delivery load the CS and SS register with the values delivered from IA, okay? To determine and load a CS register. It is expected that operating system will set IA star to 00B to 00 byte and star to 11 byte. Okay. So I guess what they're saying is that Fred will still use the same standard way that star uses it. Okay. But there's some expected bits. Okay. AI kernel GS base, existing use. The swap.gs instruction, exchange the value of this MSR with the base address of the GS segment register. Okay. Okay, so this is a register that exists, and the swap.gs instruction will swap this with the GS. Okay. And it's only the base address of the GS segment register. So it's part of it. So can we have the GS register anywhere? Like they don't describe it in here, right? Anyway, I don't believe that it's that important. Thread use execution of the RE of the event return user perform the same swapping operation as it does a thread event delivery event that arrives in ring tree. Okay, I'm not sure if I understand that, but who gives a shit? PL0 SSP. Okay, that's just shadow stack thingy. Okay, we need to read this. I'll go sneeze again and pee. Give me half a second. And we'll get to an understanding of this shit, okay? We need to. Read it. Test. This is a new test. Okay, you're testing your thing. Cool. Yeah, of course I'll read it. I'll read everything. Thread event delivery. Or, oh, were you talking about this? Oh yeah, maybe. IA32PL0SSP. Existing use, the shadow stack feature of control flow enforcement technology, CET, typically loads the shadow stack pointer from this MSR when entering rin 0. Thread transition use the MSR as IA32 Thread SSP0. And when we read it, they were talking about the last test before giving up this morning. Oh no. Are you talking about the YouTube chat thingy? Oh no. Where's your issue? Giving up programming. Yeah, I got that. Not watching the stream. The issue is my brain. Oh yeah, I got that. That's why I'm trying to relieve you of some pressure. Can do two things at once. Well, that's fair. I cannot do two things at once as well, but I know that you're talking about something else. Maybe you're asking too much of yourself at this moment, and you should choose a thing. If it is a chat thingy, I'm interested. If it's something else, I'm interested too, but maybe not. Understanding Fred and trying to make sense of Asyncyo is, in my state, is difficult. I'm assuming here that you're talking about the thing. Would you even need Asyncyo? Oh, you would need Asyncyo for um yeah, for I think I get it. Yeah. I don't know anything about that. Yeah, async things are always complicated. You're right that whenever we play the sound, it should be async, but maybe I'm retarded, but I would have done it as threading for the sound at least. Like you can just run whatever the fuck thing that does like that push the sounds to the system. You run it as a thread, so that way it will just like run the command and then relieve back to your thing. Less issues with asyncio, but less effective. I agree with you, but here I'm talking just about the part of executing the sound. So you would keep your asyncio base, and you would use thread only for executing the sound. Because right now this works. Maybe later. But thread requires more complicated IPC. I understand what you're saying. I think that you're thinking too far into how it works under the hood. And it may be, again, I don't know anything, but it may be one of those things where you just have to be like, fuck it, I don't care about how it works under the hood. I just open up a thread, send it, and ignore it. Like let it close itself when it's done, type of shit, and it just execute the sound. Because from everything that I'm seeing here, some module will need traces are between each module. I think you're getting it too far, right? Because here you could, like this is your core thing. You can check, like from, I'm assuming from here, you can check if it's an admin, you can check what type of message, you can put your ifs in there. And then all you would have to do is to make the execution of whatever does the reaction inside of a thread. So that thing is threaded, but everything else is not. So like you don't have to worry about any module of it. Like this is already further than what you need. You will see. I think we are telling the same thing. That might be. If ever you're giving up, just push it to Git and we can take a look together. I'll try to finish Fred. Fred event delivery. When the thread transitions are enabled, cr4.thread equals 1, yeah, we know that, IDT event delivery of accession and interrupt is replaced with the thread event delivery. In addition, the existing operation of syscall in sysenter is also replaced with the thread event delivery. These changes do not affect the processor handling of exception or interrupts prior to event delivery. For example, any determination that an event caused a VM exit or is converted into a double fault occurs normally. Similarly, a page fault or a debug exception update CR2 and DR6 respectively in the normal way. Okay, I think that what they're saying here is nothing changes. The principal functionality of thread event delivery is establishing a new context that of the event handler in ring 0 while saving the old context for a subsequent return. Okay, so we save wherever we are in the stack and on like the execution, so the context, I guess that's what they mean by that. We have a new place where we process things, which would make sense because I think that with IDT, like the switching of that context is way more like software heavy, where Fred would handle more of it, I guess. Okay. Some part of the new context have fixed values, while others depend on the old context, the nature of the event being delivered, and software Configuration. Section 5.1 describes how Fred event delivery determines and establishes the new context. Section 5.2 specifies how Fred event delivery saves element of the old context on the stack and, when enabled, the shadow stack. Section 5.3 then describes how additional state is updated. Section 5.4 gives detail about faults encountered during Fred event delivery. Fuck, my brain has a hard time. Appendix A.1 presents a detailed flow of the operation of Fred event delivery. Maybe I need to read this. Can I just read this and maybe get a better understanding? I can just click it, right? Can just click it. We're not savages. We're talking about one of the biggest company in the fucking world, of course. Of course. This appendix gives detailed pseudocode for Fred event delivery, event return system, and event return user. Unless otherwise noted, the pseudocode in this appendix should be considered definitive for the Fred transitions. Okay? Yeah, I'm assuming that when what they show here is what is done by the hardware behind the scene. This appendix presents the detailed pseudocode for the operation of Fred event delivery. This does not include the detail of how event information is formatted or how event data is determined. These details are in section 5. Okay, that's where we come from. Okay. Old state in temporaries. Okay, so yes, but this helps understand the values and everything. Yeah, that's perfect, right? I don't want to see what happens in software. I want to see what happens in hardware. That's the important part for us right now. Okay, so we copy essentially all of the old information. If CPL equal 3, then current stack level equals 0. Else, oh, wait, what the fuck? Okay. Old GS base. Okay, so we essentially save everything. Let's just assume that. And for some reason, stack level is 0 whenever we are in user mode. Okay. I don't know why it's inverted, but okay. Okay. Erets and ear to you will restore the old flag before saving. Event delivery updates flag. Okay. If the event being delivered is a fault other than the interruption breakpoint, or the event delivered is a trap or interrupt following the partial execution of an instruction between iteration of the return something prefix string instruction, then old flag. Okay, we don't care about that. Update bits above CS selector to old additional information. Erets and ear to you. So event return to system, event return to user, we'll use these. So we update the CS information, I guess. If CPL, so if the current protection level, or if the ring is 3, then we set old CS to 0. Okay. Updates bits above the SS selector. This is a new test for text to speech. Oh, that's cool. Oh, I would love that. STR blocking in effect. If event being delivered is either syscall, sysenter, or int, then, okay. If it's an NMI, okay, I'm not sure if I understand any of that because we're talking about SS and I don't know what SS does. Okay. So essentially we saved everything. Determine new context, determine new return instruction pointer. If old CPL equals 3, did we save CPL as what it was? Yes, okay. This is the last test for today. Based. Okay. CPL stands for current, okay, user space. Did an interrupt happen or exception happen while user space application was running? Okay. Then new rip. Okay. IA32 Fred config is, I'm so fucking retarded right now. Is the it's a bitwise not operation. So we're inverting things. Okay, fuck. Is the MSR during boot, Linux write the memory address, master? Yeah, okay, so, okay, so this is the new address that we're going to. Okay, I think I get it. Is the bitwise not operator, binary F, is 12 bits of 1. Clearing the bottom 12 bit enforces a 4 kilobyte alignment. Wait, but if we put a... Oh, it's a not on that. Why wouldn't you just put zeros? Isn't that retarded? It works, not finished. Needs security, but working for my messages. Well, that's cool. I want to test it. We'll test it after, okay? If you can push it, that would be good. Even if it's not secure, I don't care. Okay, so invert, I don't know why they are inverting. Is it just because it's simpler to determine the 12-bit thingy? I guess that is. So 12-bit, all zeros, we do a hand. Oh, it's because inverting will put 1 at the end of the thing. Oh, okay, I get it. So we cut out the bottom 12-bit. Okay. Sorry, my brain is trying. Instead of reading table in memory, the CPU calculates the entry point purely in silicon using a single MSR. By hardcoding 256 odds for kernel-to-kernel transition, the hardware allows OS developer to write highly optimize separate entry routine. Okay, so there's one way. Oh, okay, that's cool. So when you write your thing as a dev, you'll write the code to contains the code to swap CR3 patch table stack pointer and save the user space, while contains a code for kernel level exception and skips the context swapping because it is already in ring 0. Okay, so there's a difference here. Oh, that's cool. Okay, I think I get it. If new rip is not canonical relative to the current paging mode, then there's an error. Determine the event stack level. Okay, fuck. Determine events stack level in the new stack level for event handler if old CPLs equals 3 and event is not an exception nested on the event delivery and event is not, that's a user configurable that we can configure thing. Else if the event type is a hardware exception, software exception, privileged software exception, or NMI, v event vector. Okay, so then it will look into our array thingy that we took a look earlier. Then event SL will be whatever the fuck is in the array. Else syscall with CPL does not change the CSL. Okay, we're doing pretty good right now. We're doing pretty good. Pseudocode defines how the Intel, blah, 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 we don't care about that. Understand this, you know, Fred, introduce, ring 0, stack level 1, 0, 1, okay. Okay. The wording here is interesting, but okay. In modern operating, you cannot always use the same standard kernel thread stack. So if the kernel thread stack is corrupted, a page fault occurs trying to push the error code onto that corrupt stack cause a double fault. If this double fault also tries to use the broken stack, the whole system triple faults and instantly reboots. This pseudocode calculates the 2-bit values, event CL, representing the target stack level to ensure that critical events get guaranteed safe execution environment. This is the exact breakdown of how hardware routes the stack. So the standard user to kernel transition. So if yeah, it's the scenario, a normal transition from user space into kernel space. This could be a standard system call or a timer interrupting a user space application. This explicitly exclude double fault. Wait a second. Maybe this, are we talking here? Okay, there's currently no return, no like thing. So this would apply. Okay, this always apply. Okay, I think I'm understanding more. Okay, let's read again. A normal transition from user into the kernel. This could be a standard system call or a timer interrupt. Well, no. Question mark, question mark. Anyway, or timer interrupting a user space application. It explicitly excludes double fault and nested delivery errors. The result, event stack level. The CPU uses stack level 0. This is the standard default kernel stack assigned to the executing thread. Because we are coming from user space, the kernel stack is assumed to be empty, fresh, and safe to use. Oh, okay. Is that the idea? 2. Handling and external hardware interrupts. Opening a can! Hi, brother. How's it going, Rust? If event type is external interrupt, old CPL must be 0. So we're assuming 0 here. I don't know. Okay. The else implied that the CPU is already executing inside the kernel. While in the kernel, isn't that a bit retarded? Because here, if you were to assume that you're inside of the kernel, I'm looking in the wrong place. Okay. Wait, what? Am I? Where the fuck are we? We're here. Like, why would we need this part if we're assuming inside the kernel? Wouldn't those always be old CPL equals 0? I guess they need to make sure. I don't fucking know. While the kernel or hardware device like network card triggers an external interrupt. Okay. The result, the CPU reads bit 10 and 9 of the main IA32 thread config register. Why the operating system like Linux often want to handle hardware interrupts on a completely separate stack from the thread stack and to prevent deep thread stacks from overflowing during a barrage of hardware interrupts. The kernel can configure these 2 bits to tell the hardware if a hardware interrupt it's while in ring 0, immediately switch to stack level 1. Oh, okay. Okay, now it's starting to take place. Okay, I think I get it now. Okay, the IST replacement. Event type is hardware exception, software exception, privileged software or NMI. Okay. The scenario, the CPU is already in the kernel and a severe CPU exception occurs. This includes non-maskable interrupt, page fault, double fault. The result, the hardware looks at the decayed MSR called whatever the fuck this is, thread stack level. Oh well, I got it the first time. Yeah, that's our array thingy. This is a 64-bit register, effectively an array of 2-bit values for each of the 32 standard x86 vector instruction. If a double fault occurs, the CPU bit will read this. If an NMI, okay, yeah, I got this. If an NMI occur, vector 2, bit 5 to 4. Why this directly replaces the legacy IST interrupt stack table mechanism found in 64-bit TSS, a task state segment. Instead of the OS building a complex table in memory, the Linux kernel simply writes to this MSR during boot, but NMIs on stack level 3, double fault on stack level 2. The hardware pulls the stack level directly from the registered silicon, bypassing memory read entirely. All right, that's cool, but I'm not sure how it would know where to put those stacks, but I guess that's part of the magic. ... Okay, software interrupt from the kernel. Can we read else? Okay, if it's not this or this, else syscall sysenter int with CPL 0 does not change the current stack level. So current stack level is equals 0. Yeah. No, I'm retarded. Okay. Else syscall sysenter int with CPL equals 0 does not change CSL. Okay. A kernel thread deliberately trigger a system call instruction or software interrupt while already inside of the kernel. Okay, so we don't change the stack level. Does not deliver the stack level because this is planned synchronous action, not asynchronous hardware emergency. Okay, cool. Fuck, that's garbage when it's written like that. Tried having an idea. All right. We're getting there. We're getting there. Okay, so we just did this thing. So let's read it. New current stack level should be the max between event stack level and old current stack level. Okay, that makes sense. So that's why everything is 0 unless something is fucked up or unless we have an external interrupt, which we can choose whatever the fuck that is. Okay, okay. I fail to understand why this is important. Like, I get what they write somewhere here. Okay, let's go on. Let's go on. So, new stack level. Determine the new return stack pointer. If old CPL equals 3 or new CSL is greater than old CSL. What the fuck? Oh, if we are in the user space. Okay, cool. If we are in the user space or there's a change, wait, yes, or there's a change in our current stack level, then new RSP, so the new return stack pointer, will be the thread RSP, where I is the new CSL, so it's the change CSL. Okay. Else, decrement RSP as specified and align to 64-bit. Okay, so go down in your stack. So new RSP instruction to, yep, will do. I'll prioritize this. I know we both want this. Else, decrement return stack pointer. Okay, so if we are already in kernel mode, we can just go down a little bit. Makes sense. Determine the new R flags. Clear all bit except position 1. Wait, but what if you're at... Wait. So let's say that your current stack level is 1, and then the next stack, the new stack is 0. What would happen? Okay. If old CPL equals 3, I guess that would be no, and new, that would be no as well. So all we would do is add on to it. Okay. So this only goes up. That's my understanding. The stack level only go up. When it goes back to 0, it will do this thing, and our new CSL will become back to 1 because of this max. Okay. I think I get it. Determine new R flag. Clear all bits except position 1. Okay. I don't know that. So if needed, determine the new shadow stack pointer. Okay, I truly don't think that we need to read this, but fuck it, we'll do it quick. If shadow stack enable, then old CPL equals 3. Okay, so we do the same logic that we had above. So we do the shadow stack thingy. So we're essentially doing the same thing as above, but just for shadow stack. Okay, got it. Establish new context. Old state will be restored if the subsequent exception, if there is a subsequent exception. Okay. Date, segment register, if event occurred in ring 3. If old CPL equals 3, then, goddamn, the CPU does a shitload of things. Then, set CS to standard value used by 64-bit operating system. Brain, please register. I'm not registering any fucking thing right now. Maybe I'm hungry. I don't know. Okay, update segment register if event occurred in ring 3. So if old CPL equals 3, then set CS to standard value used by a 64-bit operating system. So I'm assuming that all of this is just like a bog standard. We it reset on CS, we it reset on SS, we swap in supervisor GS base, so we swap in, we put in GS, whatever the fuck the kernel wants it to be. Okay, so this will prepare our CPU. Update register defining context. RIP equals new RIP, new flag, new RSP, new CSL. Okay, so all the values that we created, we set them in place. Save state on stack. Ooh, that's the interesting part, okay? Save return state on new regular stack. Memory access tier have supervisor privilege. Okay, so we take our backup. So push 8 byte that are all zeros, push 8 byte, event data, push 8 byte, old SS, so old information, old RIP, old error code. If supervisor shadow stack enabled and old CPL was 0, save data on new shadow stack. Wait, what? If supervisor shadow stack is enabled, okay, so if we are using shadow stack, and old CPL was 0, so we were in ring 0, save data on new shadow stack. Okay, guess this is some magical shit for shadow stack. Cool. Let's not get into this. I don't want to know about new shadow stack, so we're just like pushing zeros. And all of that seemed to be on Fred's stack because SSP, new SSP. Wait, we're currently outside of this thing. So essentially, what I'm getting from this is that no matter what, as long as we have a Fred transition, we will have that thing. Fuck, I'll reread because my brain didn't register correctly, I think. And all that seems to be on the Fred stack because of SSP, shadow stack pointer line. That might be the answer for yesterday's question, just before the comment that save stack. Oh, if we have CT enable and shadow stack enable, then the current shadow stack pointer equals the new shadow stack pointer. Okay, no issue. Fuck, let's finish this, and after that I'll make an explainer, and if you disagree, tell me, alright? We're trying to get to an understanding. RSP equals new RSP. Yeah, okay. So if we have shadow stack, save data on the new shadow stack. So this, so remember, shadow stack is like something different. It's elsewhere, and it saves data that are crucial for the CPU to review if something was messed with. So here we are expecting it to have a different address to not relate to the RSP at all, but save the same data. So store 4byte0 to address SSP -4. Not sure if I understood that. So shadow stack access. Okay, shadow stack, and so we make the boundaries. We put the old CS, old RIP, and old shadow stack pointer. So those are like the verified things. Okay, so that's to verify with the shadow stack. Cool. Update additional state. Update additional CET state as needed. So that's shadow stack again, or control flow integrity thing. Fuck. That's not control flow integrity. It's for control flow enforcement technology. I was pretty close, okay? CFI is a subset of this, for Intel at least. Okay, SSP, so shadow stack pointer was updated earlier. Cool. So if we have that value, then if the old ring, if we were at ring 3 and we have shadow stacks enabled, then adjust so bit 63 to n, get the value of n minus 1, n being the processor. Okay, so we make sure. Oh, okay, so we can create. What is this? Wait, give me a second. Yeah, the shadow stack thing we need to kind of ignore. One give you 1, you take 15. Nice one. You are memeing. Okay, Gandalf horse. Okay, the shadow stack. I don't know the lore. Okay, I'm not that kind of guy. Okay, I don't know movies, don't know books. The shadow stack make things harder to follow. Yes. Okay. Loading additional state. After, let's just read this real quick, or at least part of it. After loading the old context and other information, thread event delivery completes operation by loading additional register and updating other processor state. If the event occurred in ring 3 and user shadow stacks are enabled, so user shadow stacks, the IA32PL3 SSP MSR is loaded with the old value of SSP. The value loaded in the MSR is adjusted so that's blah, 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 blah. Okay. If supervisor and direct branch tracking is enabled, okay, that didn't help at all. What is PL in previous level? Oh, maybe. Can we get like a name on this? Give me a second. Or maybe they talk about it here. Oh, where? Where? Highlight, you dumb bitch. Okay, maybe that's a bit violent. I like it when it's like, it's somewhere. Good luck, bitch. Ah, it's somewhere. I didn't know, bro. Yeah, the computer is like, fuck you. You know what? It's hidden somewhere, and I don't know where. Do we have like a... Is it in the thinking step, maybe? No? Bro. What is this MSR register? Oh, fuck it. Or is the AI not retarded? User mode shadow stack pointer register is a user mode shadow stack pointer that is part of the control flow enforcement technology implemented by Intel processor. It's used to manage the shadow stack, which is the second stack. Hold on to. Okay, cool. This is designed for... Okay. Didn't help at all. Okay. When shadow stacks are enabled at a privilege level... Oh, that's what privilege level means. Where the syscall instruction is invoked, the SSP is stored into... Oh, okay. So that says IA32, privilege level 3. So that's user mode. Shadow stacks. Pointer. Holy! It might be because of dark mode. Yep, might be because of it. Still, you C should copy pseudocode, remove all the shadow stack reference, easier to read. I think it adds an understanding, so I kind of need to keep it in. Where the fuck are we now? Okay, we're back. So this is just adjustment to the user space shadow stack. If another type of security, then I guess we update the security. Okay, who cares? Update the event-related state. Clear any debug trap that are pending prior to Fred event delivery. If event is being delivered is an NMI, then block NMIs. What the fuck does that even mean? If the NMI was injected by VM entry, the existing treatment applies. Physical element breaking is Physical NMI blocking is not changed, but virtual NMI blocked. Virtual NMI's VM execution control is 1. Okay, fucking hell. Okay, current protection level equals 0. Okay, so now I think I get it. So essentially, each time we use Fred, we will create that big ass stack thingy. Okay, wow, what a writing. Okay, so each time that we use Fred to go from, well, it would be to go from user to kernel mode, we will create this big ass thingy. And in other cases, it wouldn't, right? So if I go look, where do we save everything? Wait, am I retarded or that's just us resetting the thing? Oh, it's after. Okay, it's here. So we always save on the stack. Okay, we don't even give a shit about who you are. We always save on the stack. So no matter who you are, we save this shit. Okay. Okay. So Fred will save a bunch of information on the stack whenever it does a transition so that it can refer to this in order to process things correctly. And if the call that we are doing requires another stack level, so if the stack level does not equal the current stack level, if it's lower, so if the current stack level and the new stack level looks like this, fucking hell, then we create a new stack. Okay. Okay, we're getting there. How about returns? I think returns will come and crystallize all of that shit. Oh, yeah. So return to system. So when we do return to system, we stay within the kernel. So this should be a quicker thing. The appendix presents detailed pseudocode for the operation of return to system. Makes sense, so I was wrong. Fred saves on the user space stack. Yes. Unless the stack level of the event that we are currently processing is different. Then it will go pull from its registers. Yes. And those, my understanding right now is that those registers are essentially empty chunks of memory, just so that we can quickly go grab them and do shit with it and not require some magical adventure through the memory. Okay, so if CR for Fred equals 0, if we don't have Fred, Oh, okay. If we don't have Fred, or we're not in long mode, or current privilege level is greater than 0, then we have an error. Yeah, that makes sense because we're supposed to be in system. Okay, that makes a lot of sense. Okay, so that's just a sanity check. Pop old state from regular stack and check it. Okay, return stack pointer. Skip error code so that RSP reference the return state. Is this the thing that we were going to yesterday? Where we had like +8s that we didn't know where the fuck were coming from? Anyway, I don't think that's it, but skip error code so that RSP reference the return state. Yep, don't look at it. Okay. So let's just assume that we're going back in the stack. We're getting back the information that we put on the stack. Then if new rip is not okay, that's like cleaning things up. Eret will not numerically increase the stack level. So returning from a thing cannot increase your stack level because your stack level can only grow whenever you go into the event thingy. It cannot go down because of that max function. So yes. Okay, so we don't need to think about increasing the stack level. That's impossible. So we use the current stack level and temp CS. Okay, temp CS is the old CS. Okay. So we look at the stack level where we were. ABT restore. Okay, I guess we're just restoring things. If shadow stacks are enabled, pop and check values from the shadow stack. Okay, so we're doing the shadow stack magic over here. Let's skip it because we're fucking retarded. Update register from return state. We were stuck on compiler explorer for too long yesterday. True who? Update register for return state. New return instruction pointer. No, new instruction pointer. Yeah, that's what it is, right? Yeah, that's the instruction that we're looking at currently. Whoops. Okay, the flags, the stack, the new CSL, so the current stack level that we have calculated here. If cr4.cet, so if we have shadow stacks, we set the stack, the shadow stack. Okay, so CT magical things, update events relative to, okay. Okay, so to very simply say all of this, when we have a return to system, we just load whatever the fuck we left on stack. It's that simple. Okay, cool. If ERED begins execution with R flag TF equals 1, it will always be a single step debug exception pending after ERED's event return system, regardless of the value of the stack for R flag TF and CS. Okay, I don't know what that means and I don't care. If the VMX non-root operation with the one setting of virtual NMI, okay, they're about blockings or not blocking NMI, which doesn't make fucking sense to me, but who cares? Okay, detail operation of return to user. Okay, except, okay, pseudocode, cool. So, if Fred equals 0, if we're not in long mode, or if we're currently in any other mode but root. Makes sense. Then there's an issue. Cool. If CSL greater than 0, so if the what? I'm confused. If current stack level is greater than 0, then we have an error. I guess it's the only way, if we go back and look, the only way that we could have a higher stack level is if we execute something while in kernel mode, right? That would be the logic. So if I go here where they handle that, if CPL equals 3, then old CSL equals 0. So if CPL equals 3, the old CSL will always be 0. So in user land, CSL is always 0. Okay, cool. But then if CPL equals 3, where do we have the new CSL? Yes, okay, I think I get it. I just want to see it. So, okay, if old CPL equals 3, so that is Like that part is like assume but double verify. Like technically they could remove that, and unless there's a big fuck up, it would still work. I think that's the kind of thing where these are large fuck up events, so they double check for it. Okay, if old CPLs equals 3, then event CL. Okay, event SL equals 0. So there's no world where, so whenever you come from C, when you're this, not only will old, what the fuck was this? Bro, okay, okay. When CPL equals 3, why am I doing this? Then old stack level equals 0, and event stack levels equals 0. Okay, okay, this will help. Okay, so that's why we can do, here we are. So that's why we can do this inference. Okay. Once again, that was an actual sneeze resulting in a bleedy nose. Nice. Oh, shit. That will be hard. Okay. So, give me a minute. Okay. So if we do those checks works. We pop everything back into place. Not back into place, but we pop everything into a temporary place. We return to ring 3. Okay. Okay, no. So if, wait, what the fuck? If temcs is not a return to ring 3, middle of page 44. 54 maybe? Yeah. Yeah. I agree. The idea here is that we have I don't have the same revision. All good. No, it's all good. I found it. So the idea here is that Fred can set a stack level for, and here it's good to look at the interrupts, right? So we are using the same descriptor numbering thing, right? So our interrupt descriptor table, we can use the same thing in order to reference our interrupts. First 32, those 32 have specific stack levels that are enforced by our array. So we have a register, 64-bit, and this is used as an array that can enforce a stack level whenever running this shit. And then, the fuck did I just do? Okay, and then for those other external interrupts, they are handled by the little bit that we insert inside of Fred config, the 2 bits inside of Fred config. So this is what handle this. Okay, that's my understanding. I hope this was clear. All right, we pop everything into temporary thing. We make sure that it returns to ring 3, or else there's an issue, right? Then I guess we do some magical things here. If I guess this is a sanity check. So we check if this is sane. Set new CS standardized value to ring 3 for 64-bit mode. Okay. So we set the custom things and we put everything as it should, where it should. So we reload everything essentially. Oh no, it's not a sanity check. Return to ring 3. Downloaded version 9 instead of 4. Documentation synchronized base. Yeah, the latest version is probably the best. Okay, return to ring 3 in 64-bit. Return to ring 3 in compatibility mode. Oh, we're retards. Or I'm a retard. Okay. So we can use Fred while in compatibility mode. Not protected mode, compatibility mode. Part of IA32. So we can still run 32-bit software using Fred. And it should not change anything because the commands that we're fucking with are all commands that are part of the kernel. The kernel handles all of the things that we're looking at. So it shouldn't fuck with the 32-bit part of things. Okay, I think I get it. And here, what they're checking is are you a stack related to 32 or 64-bit? Okay. Or technically 16, but who the fuck would do that? Okay. Else, load CS using temp CS. Okay. Not sure if I get the last one. AI, come to my rescue. What is this? Oh! Okay. The scenario, the kernel is trying to return to standard 64-bit application. The math, IA32 star holds the base GDT offset for the user space. Because GDT entries are 8-bit long, base plus 8-bit points to the standard data stack segment, and base plus 16 points to the standard 64-bit code segment. Action. The hardware checks if CS and SS value pulled from the stack match those exact standard offset. If they do, CPU does not read RAM. Oh. It instantly hard-coded the internal segment register with the standard 64-bit value. Okay. So I guess here what it says is, if you don't have fancy values here, it will just set it as it should. So it's a check for fancy. The slow path fallback. The scenario, the application was doing something highly unusual, perhaps something custom with the segments. Okay. Doesn't match the standard Linux IA32 star layout. Okay. Okay. Makes sense. Makes sense. All right. If new CSL equals 1. So if we are in long mode, then return to 64-bit mode. If new RIP is not canonical to the current paging mode. Okay, so if whatever the fuck is written there is retarded, kill yourself. Else, return to compatibility mode. If what's written is retarded, kill yourself. Okay, and they set the return stack pointer here, I guess, which is not needed for 64-bit. Shadow stack magic, that checks to make sure that it's not retarded, and update the register for the instruction thingy. Wait, it's a little confusing that they call it new, but okay. And then we set everything in place. CPL equals 3. Okay, let's just read this to be sure. I'm impressed how the overall special compatibility case is taken into account. Good job, Intel, Bravo AMD. To choose to use the same specification. Yeah, I'm very happy that they choose to be together. I wonder how much, because that, I wonder, Linus Torvald is an advisor on this, right? I wonder how much hatred he spewed. No, they don't talk about it. I would pay to see the Zoom call, right? And you have, like, yeah, he's an advisor on this. So, like, what's the Zoom call where he's like, okay, fuckers, you better standardize your shit because we're not coding for you. Yes, daddy. Oh, man. Yeah, but he's part of it. We've talked about it before. Okay, let's just read this real quick. Section 5.1.2 explained that thread event delivery determines the new stack level. This determination is based on CPL, the CSL, the event type, the event vector, and whether the event was encountered during thread event delivery. The principal determination is based on CPL. Delivery events occurring when CPL equals 3 is always establish a stack level 0 unless an exception has been encountered during event delivery. In the later case, delivery of a nested exception, or double fault, if one was generated, determines the new stack level, as is done in the event occurring when CPL equals 0, and is explained by the following paragraph. Okay, so that just explains the exception. Okay, I don't care about that. I think we understand this now. So the reason why it's faster and it's better, now that we understand thread, I don't see what changed the kernel to, what had to change the kernel to. Yeah, I think we are finished with the PDF, but I think that the main issue here is adjusting in the kernel for most of the offsets that are created by the thread part of the stack, right? Because like right now, we're talking about a bunch of handling that is happening at the CPU level, at the hardware level, but the software also saves a bunch of that information, right? So the kernel doesn't only rely on the CPU to like track things correctly, but it has its own way of knowing where the fuck it is. So that's probably the the gist of it. But I guess we can go on the patch and see what is with that. Okay, can we go into Fred? Um, I don't know if they will patch that was explaining everything. Where do they talk about Fred? Back in time. Oh, we'll get there. Here we go. But I don't have Fred on my CPU. The kernel will handle stack differently depending on the CPU. Yeah. Has that ever been an issue? Like you get that the kernel will save things about the stack and about the register differently depending on the CPU already. So I don't see how a differentiation there would be an issue. Without recompiling, yeah. Seems slow. Well, no, because what you're talking about here is it's a pathway that is like set at boot time. Like the kernel, okay. Maybe it's me that has a misunderstanding, but my understanding from looking at code related to security. So when they're trying to do anything related to CET, control flow integrity, and these kind of things, what they do is they have this thing where they check something. Whoops, they check something at boot. Check something at boot, and if let's say you have Fred enable at boot, the kernel will switch like a couple of bytes inside of the code. So it will essentially, like, we could say recompile, but it's not really a compilation check. It's just essentially slotting in code inside of part of the kernel, and this will do your handling for you. So what I'm expecting here is that at boot, instead of slotting in the code for your standard IDT, it would slot in the code for Fred. So that way you don't have to have an if each time you do a thing because the right code was just dropped there. It doesn't check every time, only at boot, and selecting the right. It's not even a library, right? It's essentially just putting binary code in a specific place. Like your compiler is actually doing the calculation of the space that it needs to put in order to be able to fit like the different things. Like when we were looking at this, we were looking at instructions that were essentially nothing instructions. You need a video to do a video on this. Yeah, I should. But like one of my kernel vid was essentially about that. But I should make a dedicated one. Yeah, I think it was the one. Or maybe not. It was cool. Man, has it been that long? There's no fucking way. I wasn't smart enough back then, okay? Security, please. No? Where the fuck did I talk about this? Anyway, source, trust me, bro. But source is trust me, bro. But here, believe me, the kernel has this ability to slot in pieces of code within the overall code architecture while like at boot time. So I'm assuming that Fred does this because having an if would indeed be retarded. It would be fast because it's all instructions that could be like that if could happen like within the CPU itself. It doesn't have to seek memory because you can see the state of Fred within the CPU, within CPU ID, but it would still be retarded in my view. So, but hey, I'm not a kernel dev, so who the fuck knows? Fred is a replacement for IDT event delivery on x86 and addresses most of the technical nightmare which IDT exposes. Exception cause register, like CR2, need to be manually preserved in nested exception scenarios. Hardware interrupt stack switching is suboptimal for nested exception, as the interrupt stack mechanism rewinds to the stack on each entry, which requires massive effort of the low-level entry of the NMI code to handle this. How has this changed? Wait, am I retarded? It's down there. Okay, I am. Show me the code! Okay. So if it's an NMI, we do this. But here what I'm looking at, so an NMI would create a stack. I don't see how an NMI would be in any way different. Oh, okay, I think I get it. I think the core idea here is that the NMI would have a stack level, and instead of doing the switch to a new stack multiple times, depending on the amount of NMI or the amount of nesting, it would only do it once. Even if we do a back and forth like this? I guess so. It would always use at least the same pointer, so we don't have to seek memory for it. I guess that saves time. Okay, I'll just accept the note as true. It's Thomas Gleeksner we're talking about. That's why NMI tried to disable other IRQ. I don't know if I even understand. I don't care. I think we're already so fucking far that nobody will be able to judge that part of the video. No hardware distinct, and the people that will do are just retards. No hardware distinction between entry from kernel or user, which makes establishing the kernel context more complex than it needs to be, especially for unconditionally nestable exception like NMI. Okay, it makes sense. So in IDT, here we're talking about in IDT. In IDT, we don't have the ability to know if we're currently within the system or if we're in the kernel. It disables VM NMI, right? Yes, but it also has the bit to disable NMI like outside of VM, and I don't know what the fuck that means. So that's why NMI, my brain is out. Okay, I'm not. I think that we're going down a rabbit hole that is way too deep for us, and we don't need to go there. NMI nesting caused by IRET, so interrupt return, unconditionally re-enabling NMIs. Like, I don't get that. Okay, so I guess the idea is that an NMI cannot be interrupted. So once an NMI is on the core, it disables NMIs. Okay, I think my understanding is getting there. Okay. Which is a problem when perf NMI takes a fault when collecting a stack trace. Okay. Yeah, I'm not sure if I'm understanding this. I don't give a shit. Partial restore of ESP of when returning to a 16-bit segment. Are we talking about a specific register here, or we're talking about a stack pointer? Okay. So we okay. So this fucks with the stack pointer as well. Good lord. Limitation of the vector space, which can cause vector exhaustion on large system. Yeah, we're talking about vector space on the IDT, okay. Inability to differentiate NMI sources. Okay. Fred addresses the shortcoming by an extended exception stack frame, which causes the CPU uses to save exception cause registers. This ensures that the meta information for each exception is preserved on stack and avoids extra complexity of preserving it in software. Hardware interrupt stack switching is non-rewinding. If a nested exception uses the currently interrupt stack. Okay, so they mean that you don't have to like create a new stack frame. Like you don't have to go somewhere else for your stack other than the current stack that you have plus your the 4 stack levels that you have inside of your MSRs, of your Fred MSRs, model specific registers. I think that's fair. I'll ask AI to make sure that I'm not retarded. The entry point for kernel and user context are separate in GS-based handling, which is required to establish kernel context for per CPU variable access is done in hardware. Okay. NMI are now, that's the swap thing that we saw. NMIs are nesting protected. They are only re-enabled on the return from NMI. Okay. I don't fucking get NMI. I hate it. So NMIs are disabled when working on an NMI. That's my understanding right now. But how was it not the case before? Like, that's what I don't get. Are we saying that is because of this? Ah, when we use iret, when we come back from an interrupt, it automatically re-enables NMIs, which fucks up everything. Oh! Can you prepare a group Discord page? Your YouTube channel? I want to join you. Well, I have a Discord. I don't know what that wording was. Hi, my friend. I'll send you the link to the Discord if you want to join. That was a funny wording, okay? That was a funny wording. All right, that's a link. Welcome to the team. Okay, so sorry, my brain melted for a bit. NMIs are nesting protected. Okay, so now NMIs for real cannot be. You cannot like do an NMI within an NMI where before you could do an NMI within an NMI because iret would disable the protection from that. Okay, I think I get it. Cool. Fred guarantees full restore of ESP. Fred does not put a limitation on the vector space by design because it uses a central entry point for kernel user space, and the CPU stores the entry type, exception, trap, interrupt, syscall on the entry stack along with the vector number. The entry code as to dimultiplex this information, but this removes the vector space restriction. Okay. The first hardware implementation will still have the current restricted vector space because of lifting this limitation requires further change to the local APIC. Okay. Fred stores the vector number and meta information on stack, which allows having more than one NMI vector in future hardware when the required local APIC change are in place. Okay, we're talking about this, right? There's one of these that are NMI. Wait, where the fuck are NMIs? Oh, here. So I guess later we're going to be able to have more. My friend, why do you use your email as your handle for your Discord? You should change that. That's maybe not the best idea. Okay, I think he left. I don't know. It's okay. All right. If you're still there, I love you. I'm not judging, okay? Just want you to be safe. Okay, NMI interrupt, non-measurable external interrupt. Okay, so right now we have only one option for these, and we're going to have more before. Okay. Boy. So, fuck, I think my brain is starting to be cooked. You know what? I'll pee. We'll set up the TTS because it sounds fun. And after that, I'll probably fuck off. But yeah, what I'll write on will be like, here's my idea for the video, right? What I would want the video to be is why it was shit, like at least the start of the video relating to this. So we're going to talk about IDT, about how it was bad. So we're probably going to have to do a little bit of research into like a situation where it was bad. Then we're going to explain how Fred works, and then we can make an example of how it's superior. Yeah. And after that, we're gonna have to do everything else. I have 1 week to get this shit over. Whew, that's gonna be a hard one. Like 1 week for the research, because after that, I don't have enough time to edit the vid. So yeah, going to be intense. All right, I'll go pee, and I'll be back with text to speech. All right, I took a quick peek, and goddamn, it's a good day to be in the market. Holy shit, that makes me happy. All right, let's do the things. So, okay, I'll get pulled the fuck out of this. So, all right, let's try. So, your local change file will be over. Oh shit. Is there a command that can tell it to shut the fuck up? Yeah, can I delete files? Okay. 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 I'll follow your... Break system packages. Break system packages. Is it because of the order? I guess it is. Well, what are the requirements? Maybe I already have them. Okay, I guess. All right. Wait, I'm quasi-retarded. Oh, we have an install thing? Or the config file? God damn. Wait, main, create config, file path. Oh, it's because I don't have the file, the path, I guess. Raise value. Yeah, that's probably it. What was the name? Print msj. Print msj. Okay. I didn't test the install. Okay. Do you have a config file that you can swing around, or we don't care, I guess? Yes, it should be in .config slash YouTube. Oh, there's a .config. I think your .config doesn't get updated for this. Thank you. Okay. And where is it expecting it? Oh, okay, it's expecting it here. Okay. Oh, okay. I get it. Cut, home, config. Oh, almost. God damn. You're making shit clean. I'm scared of getting my ears blown out, but I think we're gonna have to test. Oh no, I didn't put the...
This is a message.
Oh, okay. Okay, that's kind of cool. Okay. Wait, when it says saved. Oh, okay, I guess that's the...
Only work with my message for now.
That's fair. Oh, I like it. Oh man, I love this. So does that mean that, okay, when you say it only works with you, it's really like hard-coded your name in? What is I? Ah, okay. It's the logs. Oh, I love it. Oh, I love it. I always reuse the same MP3. Okay.
I always reuse the same MP3 file.
That's crazy. Oh, I love it. I love it.
Yes, only message from at me where.
Oh man. We're going to hard code this one, okay? We're going to hard code the MB where pronounced correctly. um, oh, that's cool. Oh, I like it. God damn. Wait, I want to see how you wrote this. Okay, so essentially it says where to go look in there. Okay.
No, we will have a full security thing. Look at the readme.md to see how I want to do thing.
All right. Oh man, I'm gonna be so lazy from now on. I fucking love this. Ah, I'm gonna be so lazy. I love it. YouTube Chat Monitor is a Python-based bot designed to monitor YouTube live chat in real time. It provides a modular architecture that allows users to create custom modules for processing chat messages and executing commands. The bot also includes a security system with user groups and permission to control access to the command. Installation. Clone the repository, git clone, to navigate, blah, blah, install. Okay, that's all the things that we did. And run the bot. Replace channel ID with channel, blah. Okay, that's cool. Oh, it uses channel ID and not, it doesn't use the stream ID? If so, that's kind of cool. I didn't know that was possible. The bot will start monitoring the live chat for the specific channel and execute messages and command. It uses the stream ID. Okay.
It used the streamed.
My mistake in that. I need to be lazy. I love it.
My mistake in the doc.
I love it. I'm too excited and I love being lazy. Holy shit. The config .ml in the config folder from the user zone. We're gonna be able to give Nigma such a shitty voice. No. I'll make it 3x and lower the sound. This part of the doc isn't right anymore. Okay.
This part of the doc isn't right anymore.
Holy shit. You have a full view of this. Of course, there's LLM into it. Who cares? We love it. Predefine commands. I love this, okay? I love it. I love it already. I love it. Ooh boy. We'll fuck with this a lot, okay? We'll fuck with this a lot. I just like the fact that I'll be able to be fully fucking locked in. And I'll have the message. I won't even have to give a fuck about the chat anymore. I'll just be speaking to you. I'll be speaking to you. All right. That was fun. I'll go eat and I'll think about working as I should because this needs to be done. So just putting myself a target for tomorrow. Tomorrow we should have fully locked in a full explanation from A to Z for Fred. And when I say that, I'm assuming that we will have explained why IDT is bad, why Fred is good, the change that happens today, and then we'll pass to something else. Then we need to get pretty fucking far in the kernel thing. So if we could like speed run the fuck out of it and like get there by the time I rage quit stream, that would be good. So yeah, that's where we are. That's where we're going to be. Love you and see you tomorrow. Well, if you're there. Bye bye.